Think about the largest thing you have ever seen: a mountain, an ocean, or the curvature of the Earth from a high-altitude flight. Now, imagine a sphere so massive that if you flew a commercial jet around its equator at 500 miles per hour, the trip would take you over 1,100 years to complete. You click because our brains are naturally wired to fail at this scale, and you want to see exactly where that failure begins. Sounds like science fiction. In fact, this is the brutal reality of a hypergiant star. The central paradox is that while these stars look like tiny, peaceful dots, they are actually violent, reality-warping monsters that make our sun look like a grain of sand. Where are you watching from today? Let's measure the impossible. To understand the scale of a star, we have to start with the solar radius, $r_\O.$. NASA uses our sun as the standard yardstick for the universe. The sun's radius is roughly 432,000 miles. This is already a staggering number. You could line up 109 Earths across its face. However, our sun is considered a yellow dwarf. It is a mid-sized star in a universe that builds much larger engines. The first major mechanism of stellar scale is the red supergiant phase. When a massive star runs out of hydrogen fuel, its core collapses and its outer layers puff up to incredible sizes. NASA's Hubble Space Telescope has spent years tracking Betelgeuse, a star in the constellation Orion. If you replaced our sun with Betelgeuse, its surface would extend past the orbit of Mars and potentially reach Jupiter. This means the star is roughly 700 to 1,000 times wider than our sun. This 1:0,0,0 ratio is the first bridge to cross. If the sun were the size of a small marble, Betelgeuse would be the size of a two-story house. But even Betelgeuse is dwarfed by the hypergiants. The second best point to establish here is UY Scuti, one of the largest stars ever measured. NASA data suggests UY Scuti has a radius about 1,700 times larger than the Sun. The cumulative math of this volume is terrifying. Because volume increases at the cube of the radius, $V equals \frac 403 a /pi r$3. You aren't just adding space, you are multiplying it exponentially. You could fit nearly 5 billion suns inside the volume of UY Scuti. Imagine a giant glass jar representing UY Scuti. If every marble inside were a sun, and every sun contained 1.3 million Earths, the total number of Earths inside that jar would be beyond human counting. This leads to the photospheric density trap. Despite their size, these giant stars are surprisingly airy on the outside. Because their mass is spread over such a gargantuan volume, their outer layers are thousands of times less dense than Earth's atmosphere. You could technically fly through the outer edges of a hypergiant and not even realize you were inside a star, until the heat vaporized your atoms. That realization would be enough to classify these stars as cosmic anomalies. But what happened next made the size look minor. We realized that mass, not size, is the true ruler of the galaxy. As we move from size to stellar mass, the tension moves from space occupied to gravitational pressure. Wait, before we calculate the crushing weight of a blue supergiant, if you're finding this scale breakdown fascinating, hit subscribe. We're decoding the cold reality of the cosmos every week. The most massive stars aren't actually the biggest in size, they are the blue hypergiants. While red supergiants are puffed up and cool, blue hypergiants are tightly packed and incredibly hot. NASA's study of the star R136A1 in the Large Magellanic Cloud revealed a monster with roughly 265 times the mass of our Sun. This leads to the Eddington limit. This is a physical law that dictates how much light a star can emit before its own radiation pressure blows it apart. R136A1 is so massive and so bright that it is literally tearing at its own seams. It shines with nearly 9 million times the luminosity of our Sun. If this star replaced our Sun, its radiation would strip the Earth's atmosphere away in seconds and evaporate the oceans instantly. The cumulative math of this energy is the second domino. These massive stars live fast and die young. While our Sun will live for 10 billion years, a star like R136A1 will burn through its fuel in only a few million years. It is a stellar flashbulb, a brilliant, short-lived explosion that shapes the galaxy around it. NASA's Spitzer Space Telescope has shown that the intense stellar winds from these giants push gas and dust away, creating massive bubbles where new, smaller stars are born. While size and mass are escalating, the surface temperature creates an escalating severity. Our Sun sits at a comfortable 10,000 degrees Fahrenheit, 5,500 degrees Celsius. A blue hypergiant can reach over 90,000 degrees Fahrenheit, 50,000 degrees Celsius. This temperature shift isn't just about heat, It's about the color of the light. These stars emit most of their energy in the ultraviolet spectrum, light so energetic it can ionize gas across thousands of light years. The real drama lies not in the light they give, but in the gravity they leave behind. Focus is your greatest weapon. That decision to be a giant would have been enough to dominate the sky. But what happened next made the star's life look like a minor event. We realized that when these giants die, they create the very things that end space and time itself. This is the peak of the truth, the supernova transition. This is the highest informational value I can give you. A star is only big because it is constantly fighting its own weight. NASA's NU-STAR and Chandra X-ray missions track the remains of stars that lost this fight. A star is a delicate balance between the outward pressure of nuclear fusion and the inward pull of gravity. For millions of years, the giant star stays big because it is exploding from the inside out. The climax occurs when the star runs out of fuel. In a fraction of a second, gravity wins. The highest informational value lies in the core collapse. When a star like Betelgeuse dies, its core, an object the size of Earth, collapses down to the size of a city in less than a second. This collapse creates a shockwave so powerful it blows the rest of the star into space at 10% the speed of light. This is a Type II supernova. For a few weeks, a single dying star can outshine an entire galaxy of 200 billion stars. The reality of 2026 is that nucleosynthesis is 80% of the reason we exist. These giant stars are the universe's kitchens. In their final moments, they fuse elements like gold, silver, and uranium. Every atom of iron in your blood and every speck of calcium in your bones was forged inside the heart of a star that was bigger than you think. They had to be that big to create the pressure needed to build you. It proves we have created a flow that has value because it is a massive version of a hidden truth. But there is a silent trap waiting at the end of this success. Everything I just showed you about the size of UY Scuti or the mass of R136A1 is useless unless you understand the one thing I didn't mention at the start. Most people think stars are just balls of fire. That decision to ignore the remnant would have been enough to miss the point. But what happened next made everything before it look minor. We have traveled from the 109 Earth diameter of our Sun to the 5 billion Sun volume of UY Scuti and the 9 million-fold brightness of I-136A1. The resolution here is understanding that stars are the ultimate cosmic recycled materials. You now have the roadmap to the scales of the abyss. You know why the solar radius is the yardstick. You know why mass dictates the lifespan of a star. You know why the core collapse is the most violent event in the universe. The expert status only comes after the very active work of realizing that you are literally star stuff. Bring your expectations down to earth. Focus on the fact that these giants had to live and die so that you could eventually exist, so your wonder can actually take flight. But there is one thing I did not mention at the start of this video regarding neutron stars. In 2026, NASA's NICE mission is proving that when a giant star dies, it leaves behind a corpse so dense that a single teaspoon of its material would weigh 1 billion tons. The giant becomes a midget, but its power is magnified 1 trillion times. This is the ultimate condensed version of a hidden truth. Navigating the transition from amazed spectator to cosmic thinker is the hardest part of the journey. It requires you to stop being wowed by the big numbers and start being curious about the cycle. If you can master this perspective, you won't just see a dot of light. You'll see an engine, a kitchen, and a graveyard all in one. You have the data and the framework. Now you just need the discipline to keep looking up as the next generation of NASA telescopes reveals the next layer of the dark. A star is never just a star. It is a promise of what the universe can build when it has enough room. The scale of a star is staggering, but the objects they become after death are even more terrifying. Watch this video next. It shows you the exact physical breakdown of what happens when you cross the event horizon of a black hole. Click it now and I'll see you there.